Here are solutions to homework set number 13 for ECE 111, Intro to ECE. In this homework set, we're looking at complex numbers and phasors. Now, in electrical computer engineering, we deal with complex numbers all the time, probably more than pretty much any other major. The reason is, anytime you're dealing with a sine wave, I've got two unknowns. I've got sine and cosine. Complex numbers give you 2 degrees of freedom. Second way to express complex numbers is in polar form, amplitude and angle. That's kind of what shows it better. And personally, I prefer polar form in lab. I prefer rectangular form in computations, but the two are equivalent, kind of switch between the two. As an example, here's the first problem. I've got a voltage and a current waveform. Express voltage and current in terms of phasors, and find the impedance, voltage over current. So what I like doing is in phasors, cosine is 0 degrees. So when a cosine is, well, if this is a cosine waveform, the peak would be at t equals 0. This is actually delayed by that much. That's my phase shift. Call it B. The peak is the amplitude, so I know that the voltage is in the form of A at angle phi. Polar form works out easier. The amplitude is the peak, and the delay is the angle. We actually minus for delay. To figure out the delay, find at one period. So this right here is 360 degrees. This is the delay. What percentage of the period is the delay times 360? So to do that, for the voltage, I know the peak is 8 volts. The period is 10 milliseconds. The delay is 3.2 milliseconds. So the phase is that percentage of a period times 360 minus 115 degrees. There's your voltage. Current, same thing. The current, the peak is 10 milliamps. The delay is that much, 6.3 milliseconds. The period is still 10 milliseconds. So the phase is that percentage of 360 minus 226 degrees. So there's the phasor representation of the current. The impedance then is just voltage over current, taking the ratio of those two complex numbers. That's the impedance. This is a 0.8 ohm resistor at an angle 111 degrees. That's problem 1. Problem 2 is, suppose I have an RLC circuit. What's the total impedance? Well, here I've got, these are in series, they add. These are in series, they add. Parallel, series, parallel. In series, what I get is R1 plus R2 is the total. In parallel, it's 1 over R1 plus 1 over R2. Inverted is the net resistance. So the trick is doing parallel and series. This is where it really helps to have an HP calculator, or calculator that does complex numbers. My personal favorite is the HP42 calculator, but that's been out of production for 20 years. The HP Prime is still in production. To use RPN mode, I've got to go Shift, Settings, Entry, RPN. So it's algebraic RPN. RPN is way, way, way better. To put these in parallel, I take the first one, 350, I 300. There's the first resistance. In parallel, they add as the inverses, so take the inverse. Now 400 minus J 450, 400 I 450 with a minus sign. Take that inverse. In parallel, the inverses add. Now take the inverse. These together are 362 plus J 22 ohms. That's in series with minus J 250. So add 0 minus I 250. In series, they add. In parallel, the inverses add. So take the inverse, 150 plus J 200. Take that inverse, add the inverses, take the inverse. All this is now 190 plus J 85 ohms. Add 100 to it, 290 plus J 85. That's pretty easy to do with the RPN calculator. Really tough with a sharp or TI calculator, or Casio. It's kind of why I highly recommend HPs. In my opinion, HP calculators are worth about 10 points on a test in Circuits 1. They give you the right answer. The right answer is worth points. They quickly let you grind through a problem. Speed is worth points. So again, what I'd recommend is get used to HP calculators. You're going to appreciate them when you get to Circuits 1. But anyway, here's the problem, and the answer is 290 plus J85 ohms. Similar one. Find the total impedance for this circuit. So these are in parallel, series, parallel, series, parallel, series. The entries for that. The net result should be 85 plus J77 ohms. Okay, so that's one use of circuits. Here's a voltage node with phasors. Suppose I have this problem. I want to find out the voltages at V1, V2, and V3 at two different frequencies. If the input is DC, 10, then for capacitors, the impedance is 1 over j omega c, omega 0, so this is infinity. That one doesn't matter, this doesn't matter, that doesn't matter. The current is 0. I don't have to worry about adding 0 current. Once I convert the capacitors to impedance, I can now do voltage nodes. This node I know right away is 10. At this node, the currents have to balance, so the current left, current down, and current right have to add to 0. There's also this fourth current, but I know that current is 0. I don't have to worry about 0 current. So at this node, it's V1 minus V0 over 30, plus V1 over 200, plus V1 minus V2 over 40 equals 0. At node 2, same thing, current left, down, and right add to 0. Node equation at V2. Node 3, the current left and down equals 0. Current left, current down equals 0. There's my 4 equations for unknowns. Now, going back to linear algebra, I can solve 4 equations and 4 unknowns by putting this in matrix form. So the trick is to group all the terms, place that in matrix form, and what I like doing is, as a reminder, the way I wrote this, V0, V1, V2, V3, the first column is times V0, second is times V1, V2, V3. So for example, this last equation, minus 1/50th V2 is right here, plus 1/50th plus 1/400th V3 equals 0. And likewise, the other equations translating to matrix form. So here's my basis matrix. Here's my A matrix. The voltage is inverse of B times A. So inputting B, here I did it as 4 different rows, stack them all together. When you're done, that's B. A is just 10, 0, 0, 0, 0. The voltage is inverse of B times A. There's your answer. This is why you take Math 129. Solving 4 equations for unknowns is really a pain. Unless you use matrices, then it's pretty simple. The trick is to set up the matrices. If I go into Circuit Lab, I could build the circuit, find the voltages, and I wind up with exactly the same answer. So I did the problem correctly. Next, suppose the input is a sine wave. This is where phasors come into play. The impedance of a capacitor is 1 over j omega c. So here C omega is J3, or 3. So there's the capacitance, 1 over j omega c, minus J66 ohms. This one is minus J55 ohms, minus J47 ohms. Now to find the voltages, same procedure as before. I've got 4 unknowns, write 4 equations for 4 unknowns. This guy right here is 0 minus J10 in phasor form. The real part is cosine, minus J is sine. So since this is a sine wave, that's minus J10. At node 1, same as we did before, currents have to balance. Current left, current down, current right equals 0. Exactly the same equation we had before, but I now have this extra term. So same equation we had before, but I now have V1 over minus J66 ohms. That has to be 0. At node 2, same as before, but I now have this term, V2 over minus J 55 ohms. At node 3, I get this third term, V2 over minus J 47. 4 equations, 4 unknowns. Now these are equations with complex numbers. Matlab doesn't care. So same as we did before, group all the terms, put it in matrix form, and just have these extra terms coming in. And that's a minus J10. So here's your B matrix, here's your A matrix. There, I fixed it, got the minus J10 in there. Solve, here's your answer. Now in phasors, the real part's cosine minus J is sine. What this represents is 0 cosine, 10 sine, minus 2.3 cosine, 5.3 sine, minus 2.6 cosine, 1.6 sine, and so on. So this is the voltages V0 through V3. Again, not a problem if you don't mind matrices and using Matlab. I can handle sine waves just as fine, just fine. I'm going to get complex numbers though. The reason for that is with a sine wave I have cosine and sine. In phasors, the real part's cosine, minus J is sine. Finally, to check in circuit lab, if I take the magnitude, this is the magnitude of the voltages. If I plot it in circuit lab, here's the voltage V0, here's V1, V2, V3. Move the cursor around to pull up the peak. The peak will show you what they are. I can pull it off the graph. Here's the peak I got from circuit lab. That basically matches up what I calculated. There's also an angle complex part. The angle's the delay. So these are all have different delays, different angles. That'll show up as well. So that is homework set number 11. Correction, that is homework set number 13 for ECE 111.